And welcome back. As we continue our cosmic journey, we're going to continue looking at Earth, but this time let's go ahead and go upward to look at our atmosphere. So when we start talking about Earth's atmosphere, it's best to kind of think about our atmosphere and our relationship with it as we are living kind of at the bottom of an ocean of air that really envelops our whole planet. So our atmosphere, weighing down upon Earth's surface under the force of gravity, exerts a pressure at sea level that scientists define as 1 bar, which is a term that actually comes from barometer, an instrument used to measure atmospheric pressure. Now, a bar of pressure means that each square centimeter of Earth's surface has a weight equivalent to 1.03 kilograms pressing down upon it. Now, humans have evolved to live at this pressure, make the pressure a lot lower or higher, and well, we tend not to function as well. Now, the atmosphere is divided into several different layers, and so let's go ahead and look at the first of those, which is the troposphere and the stratosphere. Now, most of the atmosphere is concentrated near the surface of Earth, within about the bottom 10 kilometers where clouds form and airplanes fly. Within this region, the troposphere, warm air heated by the surface, rises and is replaced by descending currents of cool air through convection. This circulation is actually what generates clouds and wind. Within the troposphere, temperature decreases rapidly with increasing elevation to values near 50 degrees Celsius below freezing at its upper boundary, which is where the stratosphere actually begins. Now, most of the stratosphere, which extends to about 50 kilometers above the surface, is pretty cold and actually free of clouds. Now, as we are, of course, looking at the different layers, one thing to keep in mind is that we also have our ozone layer, which is intermixed in here. Near the top of the stratosphere is a layer of ozone, or O3. It's a form of oxygen with 3 atoms per molecule instead of the usual 2, because most oxygen that is free is an O2 molecule. Now, ozone is a good absorber of ultraviolet light, as it protects the surface from some of the sun's dangerous ultraviolet radiation. Now, the breakup of ozone adds heat to the stratosphere, reversing the decreasing temperature trend in the troposphere. Ozone is actually very essential to our survival, though in the 1980s, that atmospheric ozone was actually being destroyed by human activities. The production of industrial chemicals that cause ozone depletion, called chlorofluorocarbons or CFCs, has fortunately been phased out, and as a result, the ozone loss that we were having actually has stopped and is reversed so that the ozone hole that was forming over the Antarctic is steadily shrinking. Now, as we move to the upper levels of the atmosphere, at heights above 100 kilometers, the atmosphere is so thin that orbiting satellites can pass through it with very little friction. Many of the atoms here are ionized by the loss of an electron, and this region is often referred to, therefore, as the ionosphere. At these elevations, individual atoms can occasionally escape completely from the gravitational field of Earth. And because they can escape, there is a continuous slow leaking of our atmosphere. Earth's atmosphere cannot hold on for long to hydrogen or helium, which escape into space. Remember, these are something that we have talked about as gases that Earth doesn't really hold on to very well. Now, atmospheric leakage is not unique just to Earth, because it's also what created Mars' thin atmosphere, and Venus's dry atmosphere evolved because of its proximity to the sun, vaporized and dissociated in water, with the component gases lost to space. So if we start looking at the structure of our own individual atmosphere, height increases up the left side of this diagram here that we're looking at, and the names of the different layers of our atmosphere are shown at right. So we have the troposphere down here, which of course is at the very bottom. That of course is what we are most familiar with. As we start moving up, we have the stratosphere, we have the mesosphere, and we have the ionosphere. Notice the ozone layer, of course, is kind of here near the upper layer of the stratosphere. In the upper ionosphere, this is where ultraviolet radiation from the sun can strip those electrons from their atoms, leaving them ionized. And this kind of curved red line is showing our temperature in Kelvin. So you notice the temperature decreases as we move through the troposphere. So it's increasing again through the stratosphere because, again, remember, those ozone molecules are creating heat. Then, of course, as we again move further up, we are decreasing. And then we start actually increasing again in heat as we move up to the ionosphere, again, because that ultraviolet radiation is stripping electrons from their atoms. Now, if we actually look at our atmospheric composition, you might be surprised to learn that it has a bunch of different things in it. At Earth's surface, the atmosphere consists at about 78% nitrogen, 21% oxygen, and about 1% argon, with traces amounts of water vapor, carbon dioxide, and other gases. Now, variable amounts of dust particles and water droplets can also be found suspended in the air. If we took a complete census of Earth's volatile materials, however, we should look at more than just the gases that are currently present. Now, when we talk about volatile materials, it's important to understand that these are materials that evaporate at a relatively low temperature. So, for example, hydrogen, helium. On a warmer Earth, water vapor and carbon dioxide actually would likely dominate the composition of our atmosphere because some of those other things, such as nitrogen and oxygen, may not be as, they'd probably be a lot more volatile in their free form. So, let's talk real quickly about some of our atmospheric origin. How do we come to have that composition that we have, that nitrogen dominates our atmosphere? Well, several lines of evidence show that the composition of Earth's atmosphere has changed over our planet's history. Scientists can infer the amount of atmospheric oxygen, for example, by studying the chemistry of minerals that formed at various times throughout our planet's history. There are three possibilities that exist for the original source of Earth's atmosphere and also the oceans. The first is that the atmosphere could have been formed with the rest of the Earth as it accumulated from debris left over from the formation of the Sun. The second is that it could have been released from the interior through volcanic activity after the formation of the Earth. And the third is that it may have been derived from impacts by comets and asteroids from the outer parts of our solar system. Well, with those three things in mind, let's go ahead, though, and think a little bit about what those do to ultimately form our weather, which is our day-to-day things. Not our climate, but just our day-to-day weather. Well, all planets have atmospheres with weather, which is simply the name we give to the circulation of the atmosphere. Now, the energy that powers weather is derived primarily from the sunlight that heats the surface. Both the rotation of the planet and slower seasonal changes cause variations in the amount of sunlight striking different parts of the Earth, which we previously talked about when we talked about, for example, the differences in the concentration of sunlight between the summer and winter regions. Now, the atmosphere and oceans redistribute the heat from warmer to cooler areas because, molecules like to find a way where they can kind of be in an equilibrium. Now, weather on any planet represents the response of its atmosphere to changing inputs of energy from the sun. Obviously, you get more sunlight, you have more energy. Now, the difference about weather and climate is two very important things, because we might hear this term climate thrown around, but it's not the same as weather. A good way to think about weather, this is the day-to-day thing. Climate, we're talking more long-term models. Climate, of course, is, as I just mentioned, a term to refer to the effects of the atmosphere that last through either decades or centuries. Changes in climate are often difficult to detect over short time periods. So if you try to figure out what the climate is going to be over like a week or a month, it's very hard to do so. But we can measure these things, so as they accumulate, we can start figuring out what their effect is going to be. And their effect can be very devastating in long periods of time. For example, modern farming is especially sensitive to both temperature and rainfall. If the temperature of the world were to drop by about 2 degrees centigrade throughout the growing season, that would cut the total wheat production by half in both Canada and the US. On the other extreme, an increase of about 2 degrees in the average temperature of Earth would be enough to melt many glaciers, including much of the ice cover of Greenland, raise sea levels by as much as 10 meters, which would flood many coastal cities and ports, and even put small islands that are populated completely underwater. Now, just as an extreme example of climate changes, we can look back to the ice ages as documentation of what this change might look like. The best documented changes of Earth's climate are, of course, the Great Ice Ages, the most recent one having ended about 14,000 years ago, having lasted in its duration for about 20,000 years. Now, these ice ages were primarily the result of changes in the tilt of Earth's rotational axis, produced by the gravitational effects of the other planets. Now, we are less certain about evidence that, at least once about 1 billion years ago, the entire ocean froze over. It's a situation referred to as snowball Earth. We are pretty certain about the ice ages because we, of course, have core samples and stuff like that we can reference to determine that these ice ages have happened at fairly regular intervals. But there's a theory, again, about snowball Earth where the entire planet once completely froze over but because we don't have as much evidence about this, it is at this point mostly just a theoretical situation.